Remember that Lewis structures are, in essence, a way to visualize valence electrons and the interaction of valence electrons. So if we want to do this and see this, we start with atoms, which means we start with a couple of things. We start with basically our symbol, and we have to know the electron configuration. When we look at the electron configuration, what we're trying to pay attention to is we are trying to pay attention to the largest, what we call the largest principal quantum number, i.e., in other words, the largest shell or orbital. So, an example. When we do this, we are looking at or treating each side of our symbol as one of our orbitals. Remember that when we look at the highest principal or the highest numbers and the highest shells and orbitals, what we always ultimately care about are s and p valence electrons, because those will always have the highest number. Even if we have d's thrown in, remember that d's are one level lower. So we always are strictly looking at the s and p's. This is also where we get our rule of 8, because in an s we hold 2, in a p we hold 6, and so this is where we get the idea of 8 electrons in our valence. Now, the second thing is to notice that we always draw our dots on a side one at a time, then we pair up and we go in a clockwise fashion. So we're going to start at the top and we work our way around. So to start with, we have carbon, symbol of carbon. Well, it's a C. So we know it's a C. So that means our next question is, what's the noble gas configuration? And the reason, again, we focus on the noble gas configuration is it gives us immediately what our valence electrons are. So remember, when I'm looking for the noble gas configuration, I look at the row. Carbon's on the second row. It's in the P block, and it's 2 into the P block. So I know it's P2. If it's 2P2, I know the previous level must be full, so that was 2S2. And I look at the previous noble gas. My previous noble gas was helium, because remember, this is my noble gas configuration, or my noble gases are in this column. So the previous row is row 1, so I have helium, 2s2, 2p2. So if it's helium, 2s2, 2p2, that means I have a total of 4 valence electrons, because I have 2s and 2p, and so basically I have 2 in s, 2 in p, but they're both 2, so 4. So I'm going to put my dots around my carbon. So I go 1, 2, 3, 4, and that's carbon, and that's how we do every single atom. So I'd like you to pause the video, do bromine as practice, verify what its symbol is, then do its noble gas configuration, then do the diagram. So you should have figured out that it was bromine. Step 2 is to figure out the noble gas configuration. So bromine is right here. That means it's on row 4. I'm 1, 2, 3, 4, 5 into the P block. So that's 4P5. I know everything else must be full, so that's 4s2 is full, and that's 3d10 is full. The previous noble gas was argon, so I should have had argon 3d10, 4s2, 4p5. Since I have the noble gas configuration, that means I better recognize that 4 is my highest number, so 2 plus 5 are my valence electrons. So if 2 and 5 are my valence electrons, that means I better have 7. So 1, 2, 3, 4, 5, 6, 7 valence electrons on bromine. Now again, so we've looked at valence electrons, or a visualization of valence electrons on atoms. Now we're going to start looking at the interaction of those valence electrons between atoms in order to represent the bonds. Now, remember that we know electron configurations are the result of, or help us or identify or recognize potential trends in the periodic table. We have all kinds of things applying. You have the Aufbau principle applying, which is the building up. If I know, and that goes back to what we just have done with the shorthand configurations. If I know my elements in 4p, my last electrons in 4p, I know everything below has to be full. We know that the valence electrons can also be determined by column number. So when we looked at the periodic table, if we were in column 7a, I know there were 7 valence electrons because 2 are in s, 5 are in p. That's 7. We know that metal atoms are generally lose electrons, and nonmetal atoms generally gain electrons, hence the difference in the charges. And this is because metals loosely hold their valence electrons, whereas nonmetals tightly hold. The number of electrons given or taken is what determines my charge. And we can see this be negative on most metals, positive on negative on most nonmetals, positive on most metals. Now, again, reminder about our valence numbers. We use the representative elements, my S and my P blocks, because S and P are where I get the magic number 8. We know that the periodic trends were what affected all of this, and that it's the electronegative difference that's determining my bond type. Okay, so we're looking at different bonds, and it really doesn't matter whether we're doing an ionic bond or a covalent bond when we're first starting out, because ultimately we need to do the Lewis dot structures for each element. Now, we're going to talk about the shortcut for the covalent bonds. So in terms of ionic bonds, we definitely do this. Now, the kicker, and this is what I tried to emphasize over and over in class, draw an arrow to show the exchange. And actually, it's not, the better term is a transfer. We have a transfer of electrons. So what we literally see is we see that electron leaving the sodium going to the chlorine. So now we want to draw them together. We want to show the change in. So I do it this way. Now, one of the things that I want you to do a little different is I always want you to add in the charge. So Na will be plus, Cl will be negative, and go ahead and put brackets around the Cl so we can specify that all of those electrons are surrounding the chlorine, surrounding our nonmetal, surrounding our more electronegative atom. Anytime you do an ionic bond, this is how I want you to do it. Molecules, on the other hand, now we get to start our shortcut. Our shortcut basically involves a couple of things. The first and foremost, our shortcut involves the need to know the total, wow, that was bad, hold on. Let's undo that. Our total number of valence electrons. So these are all of the atoms involved. So let's do an example. So our example is going to be CH4 or methane. Okay, so if we need to know the total valence electrons, that means I need to remember that carbon has 4 valence electrons, hydrogen has 1 valence electron, but I have to account for the number I have. So 4 times 1, I add this up, I have 8 total valence electrons for my molecule. Okay, the next step is determining the central atom. Okay, the central atom has one of two things going for it. It is either the unique atom or it's the least electronegative atom. So let's go back to our example. We have CH4. Okay, carbon is the only one. Hydrogen is technically lower in electronegativity than carbon, but there's 4 of them. So carbon's my central atom. Next, I arrange my other atoms, however many I have, around the central atom. So that means I put carbon in the center. So now I'm going to take my other ones, my hydrogens, and I'm just going to put them around it. H, 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 and H. Okay, so the next step is now to connect them with a bond. In other words, my bond is literally going to be a dash, whoops, let's try that, a dash between the elements. So dash, 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 dash. Now, once I've put the dashes in, now I have to subtract the total number of electrons that I used. Okay, the total electrons used is 2 per bond. So let's go back to our example. That means when I look at this, okay, I have 2 electrons there, 2 electrons there, 2 electrons for each one, right? That's 8 electrons. So, do I have any remaining? Well, wait, I don't have any remaining electrons. Let's go back. Why not? Well, I used all 8 of my valence electrons, so 8 minus 8 is 0, right? And that's what I should have, because remember, hydrogen, let me put this in red actually, hydrogen only needs 2 electrons. Remember, it's a 1s1, so it only needs a second one because s can only hold 2. So hydrogen's one of our exceptions. So methane should have this Lewis structure. Let's do another one. So now we're going to look at CCl4. What I would like you to do is pause it draw it. You should be good to go until you hit 6 right here. So get everything good to there and then play the video and we'll be in the same place. All right, so what you should have done is you should have figured out that you had 32 valence electrons. Carbon has 4, chlorine has 7. I have 4 chlorine atoms, so that was 32. Carbon was my central atom because it was the unique one. I put my chlorines as a skeleton around it, made my bonds. I had 4 bonds. That's a total of 8 electrons, so I have 24 remaining. So now I have to recognize the distribution of the remaining electrons in pairs around the atoms. I need to satisfy the octet. Remember that whole idea of S and P, which was where we get the 8 from. So I have 24 electrons, so I'm going to do green, remaining electrons, so it doesn't matter. 1, 2, 3, 4, 5, 6. Well, what do you know? 6. So that leaves me with 18. Well, I have 3. They're all going to take 6, so I can kind of cheat. There's 1, 2, 3, 4, 5, 6. Now I have 12. 1, 2, 3, 4, 5, 6. Now I have 6 left. 1, 2, 3, 4, 5, 6. I've satisfied the octet. I've used up all of my electrons. I'm good to go. Now, using all our rules, there's sometimes when we break the rules. We've talked about this a little bit in class where you have atoms that do not follow the octet rule. Specifically, these are hydrogen, beryllium, boron, aluminum, phosphorus, and sulfur. Now notice that phosphorus and sulfur can have more than an octet, whereas all of these ones have less than an octet. And they can make covalent bonds, molecules, with these types. Now, where we see it with sulfur and phosphorus is in one of the examples you have as homework. Sulfur, okay, normally has 6 valence electrons. And if I form something like SF6, again, go back to our rules where we have sulfur as the central atom and we arrange everything around it, sulfur can literally make 6 individual bonds. And then we follow the same rules and we add in our remaining electrons. So sulfur has 6, fluorine has 7 times 6, which is 42. 42 and 6 is 48. I've used up 12 electrons here. That leaves me with 36. 36 over 6 gives me 6 dots each, which is what I need to satisfy the octet rule. Here are the last 3 rules that you need for Lewis structures, and these are what ifs. So we hit 7 if we run out of electrons. So if you run out of electrons, that's when we need to form double and triple bonds. You're going to see this a little bit tomorrow. You're also going to see this in the practice that you have tonight. The second what if is what if I have extra electrons? If I have extra electrons, let's actually make that a different color. If I have extra electrons, then I have to put them on the central atom. And what we've already seen, if my central atom has an atomic number greater than 15, remember that atomic number 15 is phosphorus, that's why phosphorus and sulfur are included in the previous slide, I can have more than an octet around it. So get your practice done tonight, be prepared for tomorrow.